All right, we're going to learn about our second official type of sampling distribution, and it's a distribution for the differences in two proportions. But before we do that, let's just review the sampling distribution we talked about last time. This is the sampling distribution for proportions. And basically the idea of sampling variability is if I take a sample and you take a sample and everybody you know takes a sample, we're not all going to get the same result. That's called variability. But what we are interested in is how all of our different samples would come together to form what we call a sampling distribution. So we can figure out how likely and how unlikely certain different results are. So here's an example. We're going to draw a card from a deck, standard deck. That's 4 suits. We're talking about suits right now. So it's 1/4 spades, diamonds, hearts, and clubs. And we're going to replace that card. That's important. We need our trials to stay independent. So the words with replacement mean that on every trial, on every drawing, there's going to be the same probability of choosing a club. And we're going to do this 100 times. And the question is, what's the sampling distribution going to look like? So let's start with the center. So if you go straight off the formula sheet, we see that mu, and all these letters start to get crazy with the subscripts and the Greek letters and all this stuff. But the formula is mu sub p hat equals p. That's the mean of all of the sample proportions is equal to the population proportion. Well, we know the population proportion, P equals 0.25, because 1/4, 25% of all the cards are clubs. So what this center rule is saying is, again, we all take our different samples. We are going to congregate all of our samples around the true population proportion, which is P 0.25. Okay, assuming we take an SRS, we actually do random drawing. We always have conditions, and we need to assume that these cards are being randomly picked. I'm not cheating in any way. I'm really shuffling, all that sort of stuff. Assuming we have an SRS, and this is going to be an unbiased estimator. Our different samples should congregate around the true value of 0.25. So let's move on to shape. Center shape and spread, these way back to when we were learning about socks, these were the main ideas, center shape and spread. The shape of this distribution is going to be normal if, I should say approximately normal, if, now this goes back to when we talked about what I called big binomials. Really, this is all based on a binomial situation. I'm picking card, I either succeed in getting a club or I fail and I don't. And a binomial, in order for it to be big enough, we had to have a combination of trials and probability of success that were big enough to make it approximately normal. For this, the conditions are n times p is at least 10, and n times 1 minus p is at least 10. And I, again, sometimes call 1 minus p q. But that basically just means we expect to see 10 successes and failures. Right, and if I draw 100 times, I should see about 25 clubs and 75 non-clubs. So what that tells me is that this distribution should follow an approximately normal shape. So we have the center, which is at the true value. We have the shape, which is approximately normal. That just means when all of our dots start grouping together around that 0.25, the further we get from 25, the less likely they will be, and they will kind of fill in that bell normal shape there. So what about the spread? Spread, which we'll use standard deviation, that tells us how far out do we have to go. We have these approximately 3 steps left and 3 steps right before our outcomes start to get really unlikely. So what is the spread? This goes back to the binomial also. I'm not going to derive it, but the spread, let me get rid of that. Well, the spread of this normal curve, the standard deviation, so that would be sigma p hat, meaning the standard deviation of all the little individual p hat values, all of our different sample proportions, is equal to the square root of p times 1 minus p over n, or square root of PQ over N for those of you that like Q like me. All right, so that's going to tell me how spread out, what's the standard deviation of this particular normal curve, approximately normal curve. Since I know my p-value, I can calculate this. And the square root of 0.25 times 0.75 divided by 100 is about 0.0433. So that tells me, if I were to go up to my normal curve, 0.0433, so if I start at 0.25 and add 0.0433, that gives me 0.2933. And if I add another 0.0433, that gives me 0.3366. I'm adding the entire decimal. I'm going to add that again, and I'm not going to go the other way just to save some time, but this 0.3799. And basically what that's telling me is how unlikely are certain outcomes. We don't all expect to get really close to 25%, but if I got something like 38%, that's going to be really unlikely. That's way up, three steps to the right. The further you get from 25, the less likely your outcome. So center, shape, and spread are things we can figure out. Oh, and I forgot for spread. Assuming this is the case, and the only reason this formula works is because our trials are independent. So we always have a condition, assuming trials are independent. And remember, if you aren't sampling with replacement, this would be the 10% rule. Don't sample any more than 10% of your population, and your trials will be considered independent enough. Okay, so why do we care about this? Well, we care because it allows us to determine how unlikely certain outcomes are. So in this situation, we're playing a card game with our Uncle Slick Randy, and I think he's cheating because let's say clubs are good in this game, and he's gotten 33 out of 100 that are clubs. Do we think he's cheating? In other words, what's the probability that you would get 33% clubs in a world where the mean was 25% and the standard deviation was 0.0433 and the distribution was normal? So basically all we have here is an adjusted normal calculation. This is a normal CDF where the question is, what's the probability you get 33 or more? So that's 33% to infinity. And remember, with infinity in the calculator, you can just put some really big number. And we are talking about a situation, a curve where the center is 0.25 and the standard deviation is 0.0433. I rounded that a little bit, but that'll work for right now. And if I type that in, I get about 0.032. Now, you know your Uncle Slick Randy better than I do, but that's a really small chance. There's only about a 3% chance that he could get that many clubs. So if he's trying to get clubs, he might be cheating you. We typically use, and we'll see this later next semester, 5% as the point where we start to doubt that things are on the up and up. But 3% is less than 5, so we're thinking, yeah, you know what, Uncle Slick Randy might be cheating here. So 3%, just let me show you what we found here. 3%, if I go to our normal curve, which I know the center and the spread of, and I go to 33%, which would be somewhere close to that second step. And what I found was this area out here, which is about 3.2%. All right, so all that's to review what we did last time. This is a sampling distribution of a sample proportion. And now we're going to learn our second type, which is just a tweak of this one. All right, so let's talk about our newest sampling distribution. It's for the difference in two sample proportions. When we start doing stats, a thing that we're going to want to do is compare two proportions, right? The percentage of people in our country that X versus the percentage of the people in another country that whatever, fill in the blank. The percentage of people in our state versus another state, our school versus another school. You're always going to be comparing to, a lot of times you're going to be comparing to different populations. So in this case, we're going to start with two populations. Let's just say students at school 1 versus students at school 2. And let's let these population parameters, P1 is going to be the proportion of all students in an AP class. And let's just say, we're assuming we know that at this point. Let's say that, I don't know, 0.2, there's 20% of students in this school are in at least one AP class. And this would be proportion of students at school 2 in an AP class. And let's say that that's 18%. So we have two different schools. We have a certain percentage of each school enrolled in one AP class, at least one. So the question is, if you were to choose from both schools, how would those two numbers compare? I'm going to just keep it simple with the numbers and choose 100 from each school. I'm going to find my two sample proportions. The one from school 1 is probably going to be close to 0.2, and school 2 is probably going to be close to 0.18, but we know it's going to vary. We're not all going to get the same result. You might even get a sample at school 2 that's bigger than school 1. But we're going to find two separate proportions and subtract them. And now that's my individual data point. I'm going to put that on a graph and start to see what all those little differences look like. So what would all these differences look like? So I'm going to run through the same things we just did for one proportion, but do it for a difference in two proportions. If you look at your formula sheet, mu sub P1 hat minus P2 hat. So the average of all the different little individual differences is P1 minus P2. So that's just like what we saw earlier. If we are unbiased and we really do random samples, on average, I should get a curve, I'm giving away the shape, sorry, that's centered at 2%. Because if I have one group that's 20% and another group that's 18%, and I subtract the two, on average, I'm going to get 2%. It just makes sense. It's centered where it should be centered. All right, so that is relying on a simple random sample like it was before. Shape. All right, so I've already given you the shape. The shape is approximately normal. Get that word approximately in there. It's approximately normal if N1 P1 is at least 10, N2 P2 is at least 10, N1 Q1 is at least 10, N2 Q2 is at least 10. And that may seem like a lot, but that's really what we did on the last screen, is just we have two different proportions, so we have to check for expected successes and failures to be at least 10 in both in order for this to be a big enough sample. So I would expect out of 100 students, 20 and 80 to be my breakdowns of students in and not in an AP class. In the other school, I would expect 18 and 82. So both of those, all four of those numbers are at least 10. So we're good to go. So this is going to be an approximately normal sampling distribution of all the differences because all expected, I'm going to put that in word form, all expected successes and failures are at least 10. So we know we have a normal curve, and that's going to allow us to do a normal calculation in just a minute. So last thing, what's the spread? It's very important to know how spread out your normal curve is. What's the distances between these little red marks that say, what makes something really unlikely or not that unlikely? I know I'm centered at 0.02, but that could mean a lot of things. Maybe the spread, the standard deviation is 1%, or maybe it's a fraction of a percent. Maybe it's more than 1%. We don't know. So spread of the sampling distribution of the difference in sample proportions. Here we go. This is a big one. Sigma P1 hat. This is on your formula sheet, by the way, in your notes and on your AP exam. I'm just going to go right to the Q's on this one. So this would be P1 Q1 over N1 plus P2 Q2 over N2. All right, so this is PQ over N. Remember, this goes all the way back to the idea of variances add. We could derive this. That'd be another 5-10 minute video. But variances add. So even though I'm subtracting these two proportions, that's a plus in the middle. And that's because variances add, the phrase you've heard me say a million times this year. So for this particular distribution, this would be a big square root, which looks like that. Just filled in the 20%, 80%, 100, 18, 82, and 100, and that is 0.05. Let's just call it 0.55. We'll round it off there. It's about 5.5%. So that tells me on this curve how to label these. If I start at 2 and I go up 5.5%, that's 0.075. And then up another 5.5% takes me to 0.13. If I go the other way, that tells me how low to go before it gets rare. Negative 0.035 minus 0.055 is negative 0.09, so about negative 9%. So it doesn't look like, crossing over 0 in this case is not that, it's pretty easy to do. We're actually going to cross over 0, which is my next question. That looks like it's somewhere in this area right here. So here's my follow-up question, and we'll end this one. This is the center shape and spread for the difference in two proportions. Why do we need to know that? So let's say we're picking from these two schools, an 18% and a 20% chance of success. What's the probability that if we choose 100 from each, then we will get actually more students in school 2 that are in an AP class? Well, if you look at that, that's on the left-hand side of this graph. This is what I'm looking for in this case. That area right there. All right, if you cross over 0, that 0 is the break-even point. Now, more than often, we're going to get a positive number, because if we're picking from a 20% population, then more than often will be higher. More often than not, it'll be higher than the 18% school. But doesn't look like it's all that unlikely to where we'd actually get a negative, where we'd get more people in school 2. So let's calculate it. This is a normal CDF. How do we know we can use normal? Think about it. We know we can use normal because all the successes and failures are at least 10. That was what we did up there with shape. So the question is, when we're talking about that break-even point, we're going to go negative, big number, up to 0, in a distribution that is centered at 2%. Everything's in decimal here, 0.02, and has a standard deviation of 0.055. And that would be about 0.358. So it actually is not that difficult at all to get a higher percentage at school 2, and therefore a negative answer when we subtract the 2. So just to review our newest sampling distribution, center is at the true difference. If your true difference is really 2%, 20 versus 18, then your curve will be centered at 2%. This curve will be normal as long as the expected successes and failures, NP and NQ, for both samples are all at least 10. And it'll have a spread found by this big square root formula down there. That lets you fill in the standard deviation portion of the normal CDF, and it lets you know how unlikely it is to get further and further away from 0.02. So there we go, our second standard deviation.